Hello, everybody. My name is Ito. I'm going to be talking to you today about a system called Orchard. This is work with my great collaborators at the University of Pennsylvania, Hengchu Zhang, Andreas Haeberlen, and Benjamin Pierce. So I'm going to start with a motivating scenario where we have a large company such as Apple, which wants to build some extra facilities in locations most convenient to users. So I'm going to assume that users will have some sort of way of uploading their location. And it's necessary for this company to aggregate and do some sort of computation over their user's actual location, which is why I call them the aggregator for the rest of this talk. Now, if we had a central database, I could run some simple clustering algorithms such as k-means to find, say, the two most central locations to these users. To remind you of what k-means look like, we're going to have some random initial cluster centers, and then over a period of multiple rounds, the centers will become more accurate until they're a good estimation of the user's locations. But there's a big wrinkle here, which is that we don't want the aggregator collecting all of these user locations directly. So what do we want? We'd like to leave raw data on users' devices and run some sort of distributed protocol to compute the results that the aggregator wants. We want a strong formal privacy guarantee, and we're going to use differential privacy, which is the gold standard right now. So differential privacy is a mathematical guarantee. It allows for the observation of general trends in a database while bounding the information that can be learned about any one individual. And this boils down to adding noise in carefully calibrated ways. So here we'll have a bunch of users, and we want to do some aggregate computation. Then we're going to perturb the result of this aggregate computation f to get this f prime. And f prime will be distributed in such a way that it's centered at the true result, but in this way such that any adversary cannot learn too much about the presence of any individual user. So what else might we desire besides differential privacy? We want this to scale to millions or even more than a billion users. We want accuracy so that the query results are a good approximation of the location clusters. And it can be hard in practice to find an additional party to rely on for this computation, so we want to do it without any trusted party. To give you a sense of differentially private systems that can be implemented, I'm going to put up these three properties again: accuracy, scalability, and no trusted party. There is a variant of differential privacy called local differential privacy, which adds noise before aggregation. This gives us the properties that we want of scalability and no trusted party, but results in a heavier loss of accuracy. In contrast, we can do this with global differential privacy to only add noise after the data is aggregated, and we can achieve this with cryptography such as secure multi-party computation, but this only scales to the order of hundreds of users. There have also been other systems which give us both good accuracy and scalability, but do so with this any-trust model that relies on a group of servers. So last year, we actually presented a system called Honeycrisp at SOSP, which achieves all of these three properties. However, Honeycrisp comes with a big caveat, which is that it only supports one hard-coded query, which is this count-means sketch query motivated by Apple's iOS deployment. It essentially sums up local sketches. But there are lots and lots of other queries that people might want to ask. So we did a survey of the differential privacy literature to find out what kinds of queries people might ask in such a system. And we found the ones I'm listing here on the slide, which are all very different and good for different use cases. And in particular, this is the one that Honeycrisp can solve, and k-means is the one that we think the retailer might want to ask in this scenario. And this is not supported by Honeycrisp. So the question is, do we need to build a whole new system? So how do we think about this? I'm showing a version of k-means, and this is the query that our retailer in the example might use. If you look closely at this query, you'll notice that there are some parts that each node can do locally, such as finding the nearest cluster center. Some parts that can be done safely on public data, and some parts that essentially boil down to sums and counts, which is actually the very primitive that Honeycrisp can already do. And this isn't true of just this particular query. It's true for almost all the queries we looked at, and follows directly from the way that differential privacy is typically used. So even though these queries all look very different, at the heart of them, they all boil down essentially to sums and counts. So we can automatically break these queries down into building blocks but then allow us to reuse some of the primitives from Honeycrisp. We did this, and it works for most of the queries we looked at. So to give you a sense of what this workflow would look like, first, we're going to take these users and elect a small committee of user devices. This committee is because the data will be encrypted, and we don't want the aggregator to have the decryption key and be able to look at individual data contributions. So we shard the key across a small committee of user devices. I won't go into too much detail here. This is a contribution from Honeycrisp. Now, the aggregator will write some centralized query, which is translated by Orchard to a distributed query. The users will process their local data with what we call a map function, and this will then be encrypted and securely aggregated by the aggregator. Now, the committee will decrypt the final aggregate, and it also adds a bit of random noise, which is necessary for differential privacy. Now, if the aggregator wants to proceed with multiple rounds, if the algorithm has multiple rounds, the aggregator might then send more data to the user devices and start another round of aggregation and processing. But it's important that they see only the result here and never any individual data. So now that we have a high-level picture of how Orchard will operate, now I'll go through some details of how it works. The first thing I want to leave you with is a threat model. So we want to allow the aggregator to be occasionally Byzantine for arbitrary periods of time. And this is because the aggregator may have good intentions and doesn't want to mess with its own users, but then it might not necessarily fully trust itself. So it could be compelled by others, for instance, a government subpoena, to disclose data from individual users. We also assume that users are mostly correct, so a small percentage of them can be Byzantine. To understand why we make this assumption, this is lower than, say, in the Byzantine fault tolerance literature, because we're targeting 1.3 billion iOS devices. So again, in this BFT literature, we often assume that up to a third of users can be malicious, and this results in a huge amount of devices. If we even just assume 3% of devices are malicious, this is still a huge amount, 39 million, which is more than the largest known botnet. So we feel comfortable making this small percentage assumption. Now, how do we actually proceed with the conversion? So we think of programs as being composed of BMCS calls, which is representative of one entire Honeycrisp aggregation. So this acronym is composed of the following four things. One is broadcast, so this is the broadcast of any state required in between rounds. Map is, again, the local function that each user will apply to their data. Each user may also clip their data for differential privacy purposes. And then sum, which is operations on the aggregation of ciphertexts. And together, this forms one complete round of Honeycrisp. So Orchard will transform an original query by recognizing the boundaries of these different rounds, splitting them up automatically, and then reducing a program to multiple rounds of Honeycrisp. So to go through a walkthrough of the k-means query again, we're first going to elect a committee of users. There will be some randomly chosen initial cluster centers, which are sent to the users. Now, each user has some private location data. The first thing they'll do is say which cluster they're closest to. So each user will do some local computation and assign the closest cluster. And because we're going to encrypt and add up these vectors, we're going to fill in zeros everywhere else. This is all going to get encrypted with the additive homomorphic crypto system. And some clipping may also happen at this stage. So now that this has all been encrypted, the aggregator is going to use their large resources to sum up all these ciphertexts, and then pass this off to the committee, who will add random noise for differential privacy. So this is the sum of these vectors that you see here, and this is going to be perturbed slightly to get this slightly skewed result that is still representative of the aggregate user information. Then the committee will jointly decrypt this information and send it off to the aggregator for any post-processing and release. The aggregator will compute these new cluster centers, which are differentially private, and they're going to send this off in a broadcast step to the users to proceed with the subsequent iteration. All right, so now to give you a sense of this color scheme I've been hinting at a little bit, Orchard has these three different zones of computation, so red, orange, and green. And these roughly correspond to user operations of mapping and clipping in red, committee members operating on the total sum in orange, and aggregator operations, which is the broadcast. And these zones naturally exist in most differentially private query languages, not just ours. So how does this work in practice of actually processing a query? I want to show you again this k-means code. And you don't have to understand it too carefully, but I'll highlight how we actually do the splitting up. So red zone code is always operating on an individual element. So this is private data from a single user. So for example, the assign function is going to match the closest center to each user. Now data can only pass from red to orange by aggregation, so via this bsum function. And this creates these aggregate variables here. So once we have these aggregate variables, we can perform some sort of orange operations on them. And then the aggregate data can only pass from orange to green by adding some random noise to actually give it the differential private properties that we want. So now we can see that these variables are now differentially private, and we can broadcast these new centers in the clear. So a couple more things that Orchard does to improve its efficiency and accuracy. First, I'm going to show you, this is a small snippet of that k-means code. Again, I'm highlighting these bsum variables here, or functions here. This is a sum which will create these three different aggregate variables. So x, y, and size are all going to be aggregate variables that we then have to add some Laplace noise to get these new noised variables x prime, y prime, and size prime. And each one of these bsum operations naively requires a complete round of Honeycrisp. So this would mean that each user would have to take their x data point, and we'd have to do one sum across all users. And likewise, we'd have to do the same for y and size. However, Honeycrisp's choice of ciphertext mean we can actually sum up vectors instead of just summing up numbers. So each user, instead of submitting multiple numbers in different ciphertext iterations, they can just pack this into one vector and submit just one ciphertext. This means that, so now we can just perform one individual sum. So we can use this to coalesce separate VMCS calls that don't have dependencies on one another. And this can be done automatically in a procedure not unlike vectorization from optimizing compilers. One other wrinkle that I haven't brought up is that what can we do about malicious users? So in Honeycrisp, we already use zero-knowledge proofs to ensure proper encryption. But in Orchard, the fact that we now have multiple rounds of computation introduces a powerful new attack vector. So our goal is that malicious users should not be able to significantly distort the answers. I'm going to walk through an example where a user can submit a false update in between rounds to shift a facility center to wherever they want. So again, I'll show you this map with some toy user location. I'm going to walk through this 2-cluster, 3-round process. So again, we're going to initialize these 2 random clusters. After the first round, clusters are inching closer to a center. After the second round, they get even closer. And now importantly, every user will kind of receive the broadcast of these updated centers, including this malicious user who wants to move the cluster to California. So because they're aware of where the clusters are ending up close to convergence, they can position themselves in a different location, say in the middle of the Pacific Ocean, to figure out exactly where they would need to be to pull this cluster to their target. And so in this case, this is exactly what happens. The cluster gets moved to this target. So we introduce a novel defense which uses commitments and zero-knowledge proofs to ensure that the data each user uploads is consistent with itself. So a malicious user would not be able to get updated information on where the clusters would end up. They would have to commit to where they are from the start and put in to move around. Okay. So how do we evaluate this system? There's a few different types of answers that we wanted to get information about. So the first is we wanted to know how general Orchard is and whether an arbitrary differentially private query is likely to be able to run in it. Second, naively running Honeycrisp many times can be expensive. So do our optimizations significantly reduce the total costs? Third, can Orchard remain accurate for an aggregator even in the presence of malicious users? And fourth, in terms of absolute costs for the users and aggregator, is this viable? So I'm going to walk through a couple of key results, but again, the full results are in the paper. So first, we took 17 queries from the differentially private literature to get a sense of coverage. I want to first remind you that with Honeycrisp, only one query is supported, count means sketch. But now you see that Orchard can support almost all of these. So a few aren't a good fit for the computational model. But again, these are all categorically different queries. So we can expect that for most other variants of differentially private queries out there, they can likely fit into something that we can run with Orchard. So now I'm taking all the queries that we can answer here, and I want to look at the total number of BMCS calls, both with and without our optimizations. So the number of naive total aggregation rounds I would have to do relies on a few parameters such as input vector length and number of buckets for some queries. I won't go too much into details here, but we can see that with our optimizations, we severely reduce the total number of aggregation rounds we have to do and get rid of some of these dependencies. So optimizations save many total rounds. Now I'm going to show how well our robustness defense works. So this is a simulation of an attack with 10,000 total users. On the x-axis, I'm showing the total number of attackers present in the system, and on the y-axis, I'm showing the distance from the malicious target, where the attacker wants it to end up. So this is the attack success threshold of 20 miles, and anywhere below this means that the attack was very successful. So first, I'm going to show local differential privacy and global differential privacy, just these naive defenses on their own, and they don't work very well. So a single attacker can spoil this whole result. LDP does a little bit better because they're adding a little bit more noise, so it makes it harder for the attacker to figure out exactly where to place themselves, but it still decays pretty quickly. And now with Orchard, the attacker is much, much less successful, and in fact, they would have to be in a significant majority to actually get to this success rate. So there need to be more total attackers than honest present users. So now I'm going to turn to the costs of participants in the system. First, for all non-committee participants, I'm showing here the bandwidths on the y-axis in megabytes, and on the x-axis we have all the different algorithms that we tried. We can see that the cost varies a bit with query, but is generally fairly low. And we can see a very similar trend with computation. So most users will have to send less than 25 megabytes of traffic for a most expensive query and spend up to 25 minutes of computation time. If they are elected to the committee, this requires substantially more. However, for the vast majority of vast majority of users, the costs remain fairly low. I'm going to show similar graphs now for the aggregator of both bandwidth and computation. We tested 1.3 billion users again, as well as factors of 10 larger and 2 factors of 10 below. And we see that both bandwidth and computation scale roughly linearly with both the number of rounds and number of participants. So the max total cost for the largest system size requires 74 6-core machines with 2 CPUs each, and requires a fair amount of data, but this actually boils down to just 10 megabytes per user in the system, which is around 5 average web pages. And in practice, much of this can be offloaded to content delivery networks. So we see that the absolute costs are within reach of a data center. I'm going to leave you here with this summary. So our goal was federated analytics at a massive scale of millions or even more than 1 billion users with strong differentially private guarantees. Our challenges are in generality, as well as defending against a new attack vector of multi-round queries. And our idea is just to transform queries to expose these internal sums present in most of these queries, which enables our Honeycrisp style aggregation. Orchard, our solution, gives automatic query transformation with some optimizations. It scales almost linearly to billions of users, and it gives us good accuracy even in the presence of malicious users. So thank you very much for your time. You can contact me at this email, and I look forward to answering your virtual questions. Thank you very much.